Why do molecular systems work the way they do? To find out, Eindhoven University of Technology has established the Institute for Complex Molecular Systems. Let's enter the world of regenerative medicine, where next-generation smart materials are already making an impact.
So a molecule by itself doesn't have any function. It gets this function via interactions with other molecules. So I think we started more or less from the molecular sciences approach, so the chemistry approach, but over the years we have really integrated elements from life sciences, from bioengineering, but also from physics, mechanical engineering, and also mathematics. Of course, molecules are pretty central in what we do, but you can approach them from different angles, and that leads to new and sometimes also breakthrough insights in what molecules are and how they interact.
ICMS has always had an open mind for applications. For the last 20 years, teams in Eindhoven have been studying ways to replace a non-functioning heart valve with a synthetic one. The problem in young patients is that the child grows, but the synthetic cells do not, meaning a constant cycle of risky repeat operations. The solution is to put something into the body that allows the patient to grow a replacement heart valve themselves. You need a kind of scaffolding material.
And the scaffolding material that has been used successfully for this approach started off with a fundamental study about supramolecular materials that are dynamic. They are not bound via strong covalent bonds, but non-covalent bonds. They interact, and because of the dynamics, they can really change and kind of adapt to changing environments. And that's exactly what you need in the body. And based on that fundamental knowledge, people from the engineering side were able to develop this into not just molecules interacting, but really into material, fibrous material, that then was kind of processed into a matrix material on which cells could grow and become a real heart valve. You really have to have a full understanding how that structure works within the person in an in vivo situation, how you can make it in such a way that there's also no toxic effects, and that it really has the right properties to allow the cells to adhere and to grow into the desired heart valve tissue.
And now it's time for this technology to leave the lab.
Yeah, well, this is now commercialized. There's a company called Xaltis who's taking this technology really further and implementing this into the clinic. They already have done patient studies with these, successful patient studies. And now it's the next step in the further implementation of this technology to make it really accessible to a large audience. And at the same time, I think we're looking forward to the next challenge in this field of what we call regenerative medicine, which is not only to grow this kind of, you could say, this valve system, this muscle tissue, but to see if you can also create other types of functional tissues, and then you have to think about regrowing organs. So it's a parallel development of say, the molecular sciences in creating molecules and more the theoretical sciences in designing and understanding what molecules are and how they interact. But of course, we are far away from really understanding, for example, how a living cell operates. It's, I think, the holy grail of our institute and of many other institutes to really find out how all these different molecules within the cell collaborate with each other, interact with each other, communicate with themselves, but also with the outside world, to make something that is really living. And that's a process that will intrigue, I think, our type of scientists for many years and decades to come.
If you're watching this stream either live or later and have a question about what you're seeing, send an email now to questions@brabantinnovationdays.com. We're happy to connect you.